Right, cool. That is recording. So before I start with the notes, I just want to talk about why I have combined the whole class together for this topic. I think I probably briefly mentioned it yesterday. Yeah, yesterday's when I last saw you guys. I spent a lot of the school holidays watching recorded workshop videos about these new NCAA standards. So some things to keep in mind is that this level 1 program, you guys are the guinea pigs. You're the first cohort to go through these standards properly. There has been a couple of pilot schools here and there. Last year we were a pilot school, but only the EDGE class did these standards. But obviously we haven't tested out all these standards. So please be kind to any of your teachers this year. We are learning these new standards and trying to figure out what they all mean. So if we're a little bit unsure, that's the reason why. It's because we're trying to figure out how to assess these and teach these. So I spent a lot of my school holiday watching lots of workshop videos that the ministry provided with other fellow teachers and experts in the field and people that did the standards as pilots to kind of give their 2 cents on how to run these courses. One of the things I realized when I was watching these videos was that there is a huge overlap between the microbes topic and the human impact topic. And the overlap is thinking about cycles. So for the microbes people, you're really going to be focusing on nutrient and energy cycles, because understanding nutrient and energy cycles can help you justify then why pathogens are infecting our human body. Does that make sense to you guys? Do you want me to repeat that? Or are you okay? All right. Something else that I found really interesting that I learned, I know someone was interested in doing malaria as their topic. Yes? You can do it. Yeah, so you can do malaria because they are counting it as a microorganism. So you can do that one. So that's what the microorganism people are thinking about with this topic. Okay? Human impact people. I want to give you guys more free range on what you pick for the human impact, and I'll talk to you guys more individually. But again, something that's come up as a really important factor for your standard is thinking about the interrelationship of everything. So you're looking at the human impact on, one area and how that's going to affect one of the spheres of Earth, like the hydrosphere, the geosphere, that sort of stuff. But you also want to think about how that interlinks to another sphere. So we talked about that briefly in lesson 2, about how the spheres interlink with each other. And even though we're talking about the hydrosphere, the actions in the hydrosphere can affect the geosphere. Again, a lot of those interactions are related to geochemical and energy cycles. So that's why you guys are very parallel in the concept of cycles right now. I then decided that the graphene people and the phenomenon people should also sit on this lesson, because you guys are such a small group, you might as well enjoy this learning with us. We don't often get to learn as a class, and so I want to take advantage of this. So graphene people, I was thinking a lot about how you are writing your reports on graphene, and you're thinking a lot about carbon. And I was like, if you're thinking a lot about carbon, you should actually understand the carbon cycle. So that's why you guys are here. And then the phenomenon people, you guys are looking at light as your project, but light is an energy, and I want you guys to, again, think about what energy is, and this, I wouldn't say energy cycle per se, but again, we need to talk about that. So this information correlates to everybody's project, which is why you guys are all working together with this. So we're going to be, like I said, focusing on that today. Slightly different context for each group, but same overarching idea. This is also a great example because when you guys did your field trip on Monday, or some of you guys went on that field trip on Monday, I said you have to be mindful that science is very interdisciplinary. So even though you may be an astrophysicist, you do need to have knowledge about chemistry, potentially, or biology. So that's why I also want to combine this together so you guys can see that even though you might be passionate about biology, you're probably going to have to pick up some chemistry on the side. I know I had to, because I was a trained biologist. So let's talk about the cycles and some of those information. So we're going to do a general kind of overview of cycles, and then we're going to talk about the water cycle in particular, because I think that's a real core one for a lot of topics. And then we'll talk about periodic table trends, so that way we can talk about the carbon cycle as well. So, going to make some notes now. Okay. So some things that we are thinking about when it comes to these various cycles, and I know I've posted them and you guys have read them as well in your sheets. We talk about things like energy. I should say types of cycles. So we talk about things like energy. We'll also talk about things like carbon, water. What else did I want to say? Carbon, water, nitrogen. Phosphorus also, I think, came up. Oh, now I can't spell phosphorus. Let's look that up real quick. Miss Scarlett cannot spell. Can you guys spell? Hopefully better. Let me just find it. I'm just looking at the sheets that you guys, whoopsie, that's not what I want. Huh? Ah, thank you. Phosphorus. I'm trying to think what else. Do you guys remember what else had come up when you guys were doing your reading? There we go. Spelled it right. Thank you. What other cycles do you think came up when you were reading? I think those are the main ones. You might have heard of oxygen, maybe. Sulfur. All right. So, one of the things to keep in mind is that these are all things that are cycles that are part of our kind of various systems. The first one is very different from the others on the list. What is different about the bottom list and excluding energy? What do all these things have in common? They're on the periodic table. Good. So things on the periodic table are matter. Now, something to keep in mind about energy and matter is that you cannot create or destroy either of these two things. So energy, you cannot create or destroy. Matter, we cannot create or destroy. Are you okay with that? Do you need me to write that down? Are you okay? This is a common thing you guys have heard. Write it down? Okay. So, energy and matter cannot be created or destroyed. So basically what that means is that all the energy and all the matter that occurred in the Big Bang at the beginning of our universe is still existent in today's world. Now, something to keep in mind between these two things is what happens with that energy and what happens with that matter. When it comes to energy, let's change my color pens. So energy, when energy goes through our systems, it is flowing through the systems. It's going from one area to another. So this is flow. What you guys might have heard it in the junior school is transformed or transferred. I'm sorry, my messies are a little bit messy. My notes are a little bit messy. I like to do a lot of mind maps when I think. When you're talking about energy that is transformed, we are talking about energy that has changed its type of energy. So for example, you guys ate lunch, and then let's say you went out on the field and you played rugby. You have taken the chemical energy of the food you ate, and you've converted it into kinetic energy. Are we okay with that so far? All right. That energy has not been destroyed. We haven't made new energy. It has just been transformed to something else. So when we're talking about transform, we're talking about energy that's gone from one type to another. See, another. When we're talking about transferred, we are still the same type of energy. It's just a different object that might have that energy. So for example, the water is hot. You touch a hot glass of water, that heat energy is transferred to your hand and your hand heats up. It's still heat energy, but the heat energy is now no longer with the water, now it's with your hand. Are we okay with that so far? All right. Can I just move it for a second? Okay. So, one of the articles you guys were reading, look, you guys aren't level 2. I'm going to pick the biology stuff right now because the biology stuff has a good image that I want to show you guys. So let me just get that open. And that was in that second article. So the first article was all in biogeochemical cycles. I want to look at the energy flow cycles. Or energy flow, I should say. It's not really a cycle, it's just flowing. All right. One of the things you have to keep in mind about organisms is that they, for Mrs. C. Gren, require a source of food. They require nutrition. Yeah? They need that in order to do respiration, which is breaking down a food to get energy. So chemical energy to do something. Now, something to keep in mind when we are eating items is that there is energy loss is not the best way to describe it, but I would say there's wasted energy. So when you guys are thinking about the energy that's stored in a plant, and let's say the cow eats the grass. So there's energy in the grass, the cow is eating the grass, the cow is now getting some of that energy. Now, and then I go home and I have a burger and I eat the cow and I get energy from the cow who ate the grass. So that energy's been transferred. Okay? I am not going to get 100%, sorry, and let's backtrack even one step further. The grass, where did it get its energy from? The sun. So there's all these energies transfers. Now, I am not getting 100% of the energy that the grass has. All right? The reason why I'm not getting 100% of that energy that the grass has is because the cow has used some of that energy for some of its life processes. On top of it, the biggest thing that happens between the eating of different organisms, and this is what this image over here is trying to show, is that you only get a percentage of the energy. Because a lot of the energy is burnt as heat energy. We're mammals. I've actually got goosebumps right now. This is weird. But we heat ourselves. We can manage our own temperature. That's a homeostasis evolutionary thing that we've done, that we can manage the temperature that our body is at. That is actually very energy expensive. So we have to use a lot of our calories and our chemical stores to do that. That means that if something came and ate me, like a tiger, that tiger doesn't get as much energy as I got from my food because I burnt some of that energy off. All right? Are we okay with that? So when you guys are thinking about your microbes and you're thinking about their life processes, you need to think about what is our body providing for those microorganisms. A big thing that they're providing is nutrition because we're our food source. Are we okay with that as an idea? So energy is everywhere. That's kind of the main thing I want you guys to think about with that. You're being mindful that there is quote-unquote energy loss, but it's not lost in a sense that it's been destroyed. It's just become a non-useful energy, such as heat. And when you're thinking about fuel efficiency, like with cars, if you don't have a good fuel-efficient car, the energy is being wasted in heat energy usually. So the engine's getting too hot. So a lot of our energy is lost through heat. All right. The other thing we think about is matter. So matter is different when we're talking about it in a relationship to Earth systems. Matter, on the other hand, again, we are not creating or destroying matter. It drives me nuts when I'm looking at your balanced equations and they're not balanced because you're basically essentially saying the matter has been destroyed or the matter has been created. That's why you got to balance your equations. Matter, on the other hand, is being recycled through our systems. So when we look at all the different matter cycles for matter, it's being recycled in some way, shape, or form. Now, when you guys did your reading, some of the things you guys would have learned is that some of these cycles are going to be chemical changes, like with carbon, nitrogen, phosphorus, oxygen, and sulfur. Those guys are going through chemical changes, so that way they're converted from one type of carbon to another type of carbon. The other type of recycling is physical changes. So the substance doesn't change what it is, but it changes something like state or changes something like the texture or things like that. Water is a good example of something that's getting recycled, but regardless of where it is in the water cycle, it is still water. Are you okay with that so far? All right. So the other thing you guys need to think about for human impact and for microbes is you need to think about how are these acts. So for human impact, you're thinking about how are the human actions influencing these cycles. So for example, if you're thinking about climate change, how is us burning fossil fuels affecting the carbon cycle and thus creating an impact on our environment? If you guys are doing microbes, then you need to be thinking about how do these cycles come into play? Because if we remove water from a lot of our microorganisms die. And in fact, we will die if we don't have water. Water is pretty essential to life, at least life that we know. Cool. Questions, concerns, comments so far about that? All right. So next thing I want us to do then is I want us to do a little activity on water. Just go back here. All right. So we've done our notes for that one. Now we are going to talk about the water cycle. So I have an image here to help us kind of think about water and what's it doing. And we're going to design the four corners of the classroom, and you guys are going to be the pretend water molecules, and you're going to be moving around the classroom, okay? So let's assign some spots. Let's assign this corner over here to be the atmosphere, so water that's in the air. We are going to assign this corner over here to be the living organisms, so water in organisms. We're going to assign that corner over there to be water in the ground or in the land, and we'll assign that corner of the classroom to be water in the ocean or in like lakes and stuff. All right? So in a moment, you guys are going to get up and you're going to move to an area of the classroom, and then I'm going to tell you what has happened to the water, and you're going to move, then you're going to move, you're going to move, you're going to move. Okay? So, all right. Let's say you guys are starting as water in the ocean. So what did I say? Ocean's over here. So go over there. You're water in the ocean. Go to the back corner of the classroom. Okay. So you're now water in the ocean. Getting up, you're doing that. So you can tell there's a language barrier. Hey. All right. So you are water in the ocean. The sun has hit you guys. You are heating up, and you are starting to evaporate. So you guys are doing a change into what state now? Atmosphere. So you're going into a gas. So you go over to the atmosphere section. All right. I'm going to stand up so I'm not in your way. Okay, so now you guys are in the atmosphere. You are now becoming clouds. Fun fact, clouds, what state was it? Someone asked me this question yesterday. Solid or gas?
Gas.
Okay, clouds, are they, what state would clouds be in? Are they solid, liquid, or gas?
Gas.
Yeah, they're liquid. Because they've condensed. So the air in the atmosphere has condensed into clouds. So, fun fact for you guys, if you guys were wondering that one. That was a question you guys had. All right. So, you guys are clouds. You become saturated, and you can't hold that water together like that, and you're going to start raining. So, if you start raining, you are now raining into a freshwater lake. So, go back over there, because you're now in the hydrosphere again. You're going to do lots of walking. Get your steps up. I know, you guys are like, please don't make me walk anymore. All right, now that you guys are in the freshwater lake, let's pretend a cow has come by and a cow has drunk the water. Now where are you guys going? That way to the living organism. You're inside the cow now. Now you want to eat the cow. All right. Okay, now the cow has gone for a wee.
What?
The cow has gone for a wee, and the cow has peed onto the ground. Where's the water now? Over there on the ground. Go over there. I don't want to be pee. All right. The water in the ground has now been absorbed by some plants. And then the plants have just transpired, and the water has left the plants and now gone into the atmosphere. So you are now going over here. Actually, no, wait, stop. You're going into a plant, so you go over there. That's an organism. Back into a living organism. And then you evaporate over here. All right? I'm trying to think of what else I want you guys to do. And then let's say it rains again and you're just in the ground. Where you go? Back to the ground. Are you tired now? All right. Let's say there is an underground river, and in that underground river, you have now rejoined the ocean. So where are you now? Over there. Okay, you guys, I think we're done. I think you guys get the idea. Okay. So, one of the misconceptions about the water cycle is that it is like a cycle like this. Yeah? And you have to go through step 1, step 2, step 3, step 4. What did you guys realize from this activity? Is it a set cycle like that? No, because it goes back and forth, all right? So remember that these things aren't necessarily happening in a certain order. So the word cycle is a bit I wouldn't say...
Misread.
Not misread. It's not an ideal word, cycle, but it's the best we got. So take a seat. I'll talk a little bit about images and what we use as images.
I don't like it.
All right. So, the next thing I have for you guys is some images of the water cycle. And the reason why I want to show you guys these different images is so you guys can think about how you communicate your information, because it can result in misconceptions with the concepts and the ideas. This is really important for the Human Impact Group, because I want you guys to be writing letters to people in government, and how you communicate things across could influence then how people interpret it. So the first thing here, so that image before, was that a very good image? Yes or no? This one.
No.
It's quite problematic, right? Because it's too simple.
No, it's too much.
It's too much, you think? I would say it's too simple, and I would say there's a misconception because the way the circles go in like a set order. It looks like a cycle. It looks like if I was to read this, I would assume that these are the steps of the water cycle, and you have to go through all those steps to cycle through. Whereas you guys just did that activity and you didn't have to. You could go back and forth in different areas. So I found some other images just to kind of get you guys to kind of think about how you present information. Let me just spotlight this. So this one here, I would say is a bit better, because you see how it doesn't have like set circles that you need to go through that set cycle. It kind of shows each step, like these are all evaporation, this is precipitation. Precipitation can happen in multiple areas. The surface flow off, that sort of stuff. So it gives you a better idea of what's going on. I still think that there's a compromise you have to hit with a lot of your communication. So this image is better. They have put the little arrows in there as like a background thing, which again could result in the misconception that it has to go through in a certain order. So just be mindful of how you present information and what you kind of use. Just get that back. There's some other ones that I saw that I do think, pros and cons to each one. So this one over here is slightly different. We have lost the cycle kind of drawing, but there's a lot more information on there. So you can see that there's a lot more arrows. The nice thing about this is that it's showing the direction of the arrows and what it's doing. So like evaporation is going up, precipitation going down. So it's a trade-off with some of this information. All right, so that's that one that I found. And then this is the last one I found that I thought would be interesting to look at. This one again, spotlight. It has its pros and cons. So this one doesn't really have the cycle image per se, but there's a lot of noise on here. Yeah? So keep in mind that with microbes, you guys are going to be doing an expo for your project. For Human Impact, you guys are going to be writing your letters to the minister, or not minister, to someone in government. And you don't want to be too wordy, so you're going to have to use images to communicate your information. But being mindful of what images you select will influence then what interpretation people will have. So just something to keep in mind. All right? Cool. So that is all on the water cycle. We're done with that. And next we're going to do periodic table trends. So let me pass that out for you guys. And I will do one example so you guys know how to do it. Actually, I'll do one example together with you guys. I'm just trying to pick which one to do. And I'll do it. I will do magnesium. Okay. Have you guys done electron configurations? No? All right, let me walk you guys through it then. All right. In a moment, I'm going to give you guys a section of the periodic table, and I'm going to want you to do electron configurations. This is where the chemistry kids, this is where it's going to help you guys. We are talking about atomic structure. So when we talk about atomic structure, we have to think about the three components of an atom. What are the three components of an atom? Neutrons, electrons, and protons. We will do magnesium. So magnesium is number 12 on the periodic table. Its atomic number is 12. All right. Now, what is in the center of the atom? The protons and the neutrons, and we call that a nucleus. So we have our nucleus. It has our protons and our neutrons. I don't feel like I'm spelling neutrons right. All right, so they look like that in the center. And then what's on the outside? The electrons. We call them electron shells. We should also call them electron clouds. Neutrons. There we go. Confusing my physics with my biology. All right, if I'm talking about magnesium, the atomic number is 12. So how many protons would I expect in the nucleus? Nope. 12. The atomic number tells me how many protons and how many electrons. So there's 12 protons, 12 electrons. And if I want to figure out the number of protons, we need the atomic number. So let me go find that for you. Sorry, that's atomic number. Atomic mass. 24. All right, atomic mass is equal to 24. So remember, with atomic mass, that's talking about the number of protons we have plus the number of neutrons. So if I have 12 protons, how many neutrons would I have to make 24? 12. All right, so if I was to think about, I'm just going to draw this again because that wasn't very good. If I was to talk about magnesium in the nucleus, I would have 12 protons, which are positive, and I would have 12 neutrons, which have no charge. Okay? How many electrons do I have? I still have 12. I don't have any ions, so I have 12. How many electrons go on the first shell? Do you guys remember? 2. So if I was to draw the first shell of my atom, it would have 2 electrons in there. I'm going to write the shorthand, the electron configuration 2, and then I'll do a comma. How many would be in my second shell? How many can it hold? Do you remember? It's 8. Yeah, so 2, 8. So there's 8 in this shell. 1, 2, 3, 4, 5, 6. I like to draw them in pairs. 7, 8. You'll find out why in level 3 chem. All right. Do I have enough electrons yet? How many more do I have? 2. So I draw another shell, and I'm drawing 2. Like that. So this is my drawing. This is the electron configuration. It is 2, 8, 2. All right, just as a general rule, that works out to calcium. I'm having a lot of time spelling today, which is atomic number 20, is that in the first shell you can have 2. In the second shell you can have 2. How many can you have in the third shell? Do you remember? 8 as well. And then the last shell? We're going to say 2 right now. All right? Because that, if you add that up, 10 plus 10 is 20, and calcium's atomic number is 20. When you go past 20 on the periodic table, it gets a lot more complicated. You have to take level 3 chemistry if you want to know what happens after calcium. Sorry. Sorry, guys. You're not going to get the full story. But for all intents and purposes, for this year and next year, this works as a model. Okay? So when you guys are drawing electron configurations, 2 electrons in the first shell, 8 electrons in the second shell, 8 electrons in the third shell, 2 electrons in the last shell. You have to fill the first shell before moving on to the next shell. You can't just put them wherever you want. Okay? Is that all right with an instruction? All right. You guys ready to practice? Okay. So I'm just going to leave that up because I know some people are still writing, which is fine. So what I'm going to do is I'm going to give you a little strip of the periodic table, and you are going to do the electron configurations for that element. I will put up the slide with the atomic numbers so you know what atomic numbers they have. Okay? Then what you guys are going to do is you are going to compare and contrast what you guys have to figure out the 2 trends in the periodic table. There are 2 patterns that we see in there. And then we can jump into why carbon's so important. Oh, there we go. Alright, so something to keep in mind, like I said, columns all end in the same number, rows all have the same number of shells. Now, for atoms to be in their most stable state, they want to fill their shell. There are 2 ways they do this. They either gain electrons or they lose electrons. So for example, things in group 1, they tend to lose 1 electron, so that way they go down a shell and the shell is complete and they are more stable. Things in group 17 are 1 electron away from being stable, so they tend to gain 1 electron, so they are stable in their shells. Group 18, or say, when you actually look at the periodic table, they're called group 17, group 18. This one here is already stable because it has the full shells. These are known as our noble gases. They're very unreactive. Alright, so this one tends to lose 1 electron, this one tends to lose 2 electrons, this one tends to lose 3 electrons. This one doesn't do anything, this one tends to gain 1, this one tends to gain 2, 6 to 8. This one tends to gain 3, 5 to 8. What happens with the stuff in the middle? Does it gain or lose? It's a tricky one because they can do either, right? So what these guys tend to do instead of gaining or losing electrons, they then tend to make things called covalent bonds, and they share electrons. This makes it a really good building block. It's a really good Lego. Calcium, oh sorry, not calcium, carbon, right there. Carbon is the foundation for a lot of life, or actually it is the foundation of life that we know, because it is such a good building block for life. It can make lots of different structures and patterns to make lots of different molecules. So that's why the carbon cycle is so essential to what we're doing, and that's why it goes through chemical changes. So we'll see it as like I am made up of carbon, there's carbon dioxide in the air, there's carbon stored in fuel, and things like that. So we got to think about how carbon's cycling through. That's kind of giving you the basic foundation of what you guys are focusing on this lesson. All right? There is theory, this will interest you, that we could have silicon-based life. Because silicon also can do that because it has 4 in its outer shell. The issue is that it's not as readily available as carbon. It's a bigger atom. So, just some things to keep in mind. That is basically our time for today. Yeah, that's it. Hope you guys enjoyed that.